So I mentioned that the CPU needs to have a lot of conventions to be able to interact with the other components in a computer. So when I mean a lot, I mean many different types of conventions, some to deal with sound, some to deal with video, some to deal with numbers, some to deal with characters, all those different things. So I wanted to cover some of those because it might be helpful to know this to understand what the computer actually does. So this convention, as I said, covers numbers like integers, signed integers, real numbers, but also other types like characters, video, etc. So let's talk about the easiest one, the positive integers. So we are used to using decimal system to represent numbers. So what's the decimal system? Well, if you have the number 137, this really means 100 plus 30 plus 7. So we have inferred from the position of 7 that this was a unit digit, so it's worth 7. We have inferred from the position of 3 that this was a tens digit, so it's worth 3 times 10 to the 1. And we've inferred from the position of 1 that it's a hundredths digit, so it's worth 1 times 10 to the 2. And if I perform the sum here, I would get 137. Now, binary is exactly the same, except that now the weight is 2, and again, it's dependent on the position. So the weight of each digit will be dependent on its position and will be a power of 2. So the simplest number that we can express in binary is 0. So 0 in decimal notation corresponds to 0 in binary. Now, 1 in decimal notation corresponds to 1 in binary, because this is 1 times 2 to the 0. Right? 2 to the 0 is 1, so we get 1 times 1. Now 2 will correspond to 1 0 in binary, and 1 0 because this corresponds to 1 times 2 to the 1 plus 0 times 2 to the 0. And this is equals to 2. This indeed equals 2. So it helps to write things from the right. So to read this 0 first and then this one to be able to write in binary. So the 3 here corresponds to 1 1. And if I apply what I just said, I'll write it from the right first. It's 1 times 2 to the 0 plus 1 times 2 to the 1. And if you compute this, you indeed get 3. If I take a more complicated example like this one, so I start from the right, I have 1 times 2 to the 0, that's this one here, plus 1 times 2 to the 1, that's this one here, plus 0 times 2 to the 2, plus 0 times 2 to the 3, plus 1 times 2 to the 4. So okay, so this 2 to the 4, it means 4 times 4, so it's 16. And here I have 2, and here I have 1. So this is indeed equal to 19. And 32 is another power of 2, so it has a very simple expression in binary. And 57, well, we'll have some other expression that I'll let you compute, and so on. So that's for the positive integers. But as soon as you start looking also at the negative integers, things become more complicated. So the first option you have is to think, well, a negative integer is just an integer with a sign. So I'll decide to use the same encoding that we just saw for the magnitude, and then to use another bit to represent whether this this sign is positive or negative. Okay, this would work. You could have this convention. You could agree that this is your convention to represent integers, but you very quickly run in trouble with this. The main reason, or one of the main reasons, is that you have 2 different encodings for 0. Okay, you could have plus 0 or minus 0. Right? Because the magnitude will always be 0, but the sign could change, yet this represents the same number. So for instance, if you have to check equality, you can't just say that, you can't just check that all the bits are equal. You have to check that all the bits are equal, or that all the last bits are 0, and then the sign does not matter. So it becomes a bit more complicated. And if you wanted to perform addition, and it would become again complicated, because you would have to deal with, well, this large number plus this negative number of small magnitude will give me a positive number, and you would have to start putting a lot more logic into your arithmetic processing unit. So okay, so to compensate for this, 2 other methods were devised. So the first one, one's complement, simplifies arithmetic operations. So addition and subtraction. So that's simplified with 1's complement, but the problem is still that there are two zeros. So there is a positive 0 and a negative 0. And so to mitigate this, another convention was invented, and that's called 2's complement, which is used in modern computers. And this prevents both problems. So you have just 1 0, and the arithmetic is much simplified. So let's see only 2's complement in more detail. So what is 2's complement? Well, 2's complement assigns a certain value to a certain pattern of digits, and this value should be assigned integer. So it's also dependent on some number n. So in this case, I'll take n equals 8, which is a standard example. So I have 8 bits here and different patterns here of 8 bits. And these patterns, when I read them as unsigned integers, they correspond to some integers between 0 and 2 to the 8 minus 1. So this pattern would correspond to 2 as an unsigned integer. This pattern here would correspond to 130 as an unsigned integer, because this 130 is 128 plus 2. Those are powers of 2. And this explains why there's two ones here. Okay, so this is the unsigned value that corresponds to those patterns. And what I want is the 2's complement value that corresponds to those patterns. Now, that is determined in such a way that the difference between this column and this column should give me exactly 0 modulo 2 to the 8. And remember that 2 to the 8 is 256. So, for instance, for the example of 2 I had taken, well, the difference of the value for 2's complement of this pattern here should be 2 as well. Indeed, if I take the difference, I get 0, and this is indeed 0 modulo 256. So all is good. But let's look at the other example I had of 130. Now I want a value so that when I subtract it from 130, I'll get 0 mod 256. So of course the first natural guess is 130, but that will not be allowed because the value has to be small. So 130 is already too big. So the value that I should use is actually minus 126, because if I do 130 minus 126, I'll get 256, which is 0 modulo 256. So you see that this pattern here of digits will correspond to minus 126 in 2's complement. Now, why is this good? Well, it's good because the only pattern that can correspond to 0 is this one. So there's only 1 0 if you want. That's one good thing. And the other good thing is that if you think about addition, the sign does not matter at all. If you think about addition and subtraction, you could just take those and perform the operation at the level of the bits, at the level here, and you would get the exact sum in 2's complement as well. So what I mean is that addition here in 2's complement works exactly like addition for the unsigned value. So the only difference is that we're performing this addition modulo 256, just like here we would be performing the addition modulo 256, but the range of numbers between modulo 256, the range of number that we allow is a bit different. Here we allowed from 0 all the way to 255, while here we only allow from minus 128 to 127. Okay, so that was for 2's complement. The next step is to look at hexadecimal notation. So if you notice what we just did, a lot of bits were involved, so it was very hard to read. So to compensate for that, the idea is to aggregate many of the bits together into letters or numbers. So if you look at this pattern, 0, 1, 1, 1, in decimal it will correspond to 7, but in hexadecimal it will also correspond to 7. So, and so on, we get the first ones up until we get to this pattern of bits where we have a problem. In decimal, we don't usually use just one symbol to represent that pattern of bit. We use 2. We use 10, 1, 0. So instead, we'll invent a new symbol, and this new symbol will be A. And in hexadecimal, A will represent 10, or this pattern of digits. And so on, up until we get to F. So from 0 to 9 plus 6 letters gives us a total of 16 symbols. And those 16 symbols represent all the different patterns of 4 bits that you can have. So it makes it easier to read. Instead of having 8 bits, for instance, you just have 2 symbols, 2 hexadecimal symbols. Now on to the real meat, the real numbers. The real numbers are much more complicated. They're only approximations to the truth. You can never really hold a real number or give its decimal expansion on a computer. For real numbers, there are many different implementations. The main idea is always the same in modern computers, though. The idea is to bin numbers into bins, and within a bin will be all the numbers closest to a certain number of this form. So it looks complicated, but let's analyze it a bit. So the number will be signed, okay, and it will be some number that is relatively small times a certain base times to the power of an exponent. So if you want, this gives the sign, this gives the magnitude, the general idea of the magnitude, and this slightly corrects this magnitude. And then comes the question of how you balance the precision you need between the exponent and the mantissa. Okay, so just to clarify, the mantissa has some digit here that is obligatory, and then many more, and the number depends on the precision we want. The exponent will be a signed integer because the magnitude could be very small, so then we want to have a base to the exponent minus something. And in modern computer, the base is generally 2. But let's look first at the base of 10, so we make sure we understand. You might be more used to this. So this is the first example of a floating point number. The magnitude is around 10 to the 38, but I'll correct this slightly by saying it's 3.4 times 10 to the 38. In this example, I would have minus 4.028, etc., times 10 to the 23. In this example, I have 1.001001 times 2 to the minus 17. And you see that we've gone from a base of 10 to a base of 2. And this one I could have minus 1.100, etc., times 2 to the 35. And once you go to binary, there is a little gain as well. It's the fact that this number here, this digit here, has to be significant. It's what I was saying a little bit earlier. So this has to be significant, meaning it cannot be 0. But if you're in binary, that means it can only be 1. Okay? So with this in mind, here is a format example for 32-bit real numbers. So if you're doing floating points with 32 bits, you have to decide how you split those 32 bits to give some good idea of what the exponent is and some good idea of what the mantissa is. Okay, and what the sign is. So the total will be 1 for the sign. 1 bit is used for the sign, plus or minus. There's no way to do better. 8 bits for the exponent. So we can go from minus 128 to 127 in the exponent. We can't do anything of smaller magnitudes. Anything of smaller magnitude will be 0. Anything of higher magnitude will be essentially infinity. And finally, the mantissa, so this part, gets 23 digits for the mantissa, 23 bits for the mantissa. And the total here is 32. But note that the mantissa gets 1 for free because this guy will always be 1, as I was just explaining. So that's for the real numbers. But there is a lot of trouble associated with the real numbers. All we have decided so far is that we're representing any number within a certain bin by a certain convention, a certain pattern of bits. Now, the problem is that sometimes we want to perform operations on those real numbers, and we might want to add 2 of them. Now, if we add 2 numbers within a certain bin, so we have 2 bins, and we take numbers within those 2 bins and we sum them, it might be that the sum, well, it could overlap several different bins that we allow ourselves. So there has to be some convention, not just on the notation, but on the operations you can perform on numbers within this notation. And that's where there is a lot of variations between the different implementations of real numbers. So your operations could make some promises about properties that are kept when you apply them to numbers in your convention, following your convention. There's also a problem with conversions to integers. So how do you convert some numbers to integers? How do you do the rounding, etc.? So it's a very difficult topic, but it's a very important topic. Many big industrial projects have failed because of problems with real numbers, floating point arithmetic. Okay, another convention that's needed to make a computer work is a convention to encode characters. And the first convention, or one of the most prominent one, is called ASCII. You might have heard that before. So ASCII encodes using 128 different characters, 128 positions, if you want, many different characters. Okay, so it's allowing itself to the 7 bits to encode the most basic characters that it can think of. So the most basic characters are the alphabet, capitalized, the alphabet lowercase, and then some special symbols like and or numbers, of course, that I forgot to say, numbers, slashes and things like this, braces, whatever. So just some characters that you might need. Essentially the characters that you use in passwords, that kind of things. Hopefully you use in passwords. Okay, so that's a very basic encoding for very few characters. But if you are French, for instance, and you're used to writing this symbol or this symbol, that's not present in ASCII. So to compensate for this, a new encoding was invented, and that's called Unicode. And this is basically very important now because of the internet, because of all the different languages people use. So the idea is to encode characters from many different scripts. And so many different sets of letters and symbols. And there are in total 110,000 characters, and I give some examples here to show you the diversity of the things that have been encoded in Unicode. So if you want, this pattern, the information that this pattern of bit is Unicode encoded means that you can refer to a specific Korean character or a specific Cherokee character or a specific hieroglyphic, specific math symbol, etc. Or currency symbol like euros or dollars, and so on. So that's really a convention that's very important in the modern internet. There are more conventions, and also important, of course, in the modern world. So a convention for images, JPEG, GIF, PNG, bitmap, for videos, AVI, MOV, and for documents, etc. So if you are interested in those things, you might want to pick for one of your projects one convention and study a bit how it does things. That might be interesting to you. Okay, so this was for all the different conventions that a computer needs to think about. And you will see some of this might come in when you start interacting with files. But most of the time, thanks to the high level of Python, you're shielded away from that kind of things.